Good morning, dear colleagues. In this presentation, I'm going to tell you about some of the recent research in our department and lab in the field of hydrodynamics and rotor bearing systems. The presentation includes two sections. Section 1 deals with the basics of modeling using classic fluid and solid mechanics. In Section 2, I'm going to tell you about our recent experience in application of machine learning methods to modeling of hydrodynamical systems. The most common type of movement in techniques is rotation. The rotation allows to reach high speed and high power motion in limited space. Rotating parts are present in the most engines and machines. Actually, it's hard to find some machine with high speed motion without rotation, but it's much harder to find some natural rotor system. I can give you a minute to try to remember some animal who has wheels or some bird with turbine. However, rotor systems exist in nature on a micro level. The following discussion concerns the machines. The supports allow the rotating rotor to be held stationary on a fixed base. There are four basic types of rotor supports. The sliding bearings are the oldest. The rolling bearings are the most frequently used. Both types of bearings have to be in contact with the rotor while operating. The most modern type of a bearing is electromagnetic bearing. This kind of bearing is absolutely frictionless, but it's very energy intensive to carry the rotor steady by electromagnetic force. In our research, we study the fourth type of the bearing called fluid film bearing. In bearings like this, thin fluid flow helps to separate the rotor and the bearing surfaces. To generate the lifting force, which will be enough to carry the rotor, three main conditions should be met. Point 1 is that the fluid should be viscous. Viscosity is the property of material to resist high-speed deformation. Most fluids are viscous. It is easy to deform water with slow motion, but it's harder to run through the water. Some fluids has non-linear viscosity. For instance, dilatant fluids turn to solid-like materials under very high speed deformation. Non-linear properties can be achieved by adding additives to water, oils, or other base fluids. Second point is that high velocity gradient occurs due to stick conditions. Due to viscosity and small gap, the stick condition means that velocity of fluid on the surface is the same as the velocity of the surface. One may check that cooler in the computer to realize that stick condition works. And finally, point 3 is edge effect. Mostly it means that the flow channel should be convergent. If all of that pores are checked, then fluid can carry a weight, a few kilograms or a few tons. Note that some lifting effect may result in a car lift off the road, it is very dangerous. In general, fluid flow and fluid flow effects are complex in theory. Generalized mathematical model of the fluid flow includes 19 partial differential equations with 19 unknown functions. So usually we use numerical method and specialized software to solve a problem. Usually the linearization model is used to calculate lifting force. The mechanical analog of this idealization is a combination of springs and dampers. The rotor, if permissible, is considered as a material point or a solid non-deformable body. In a more general case, the rotor described by a system of PDEs similar to the equations presented previously for liquids. Study of rotor vibration is very reasonable. The gap and the fluid film is very small. The gap size is similar to a paper sheet thickness. A rotating rotor oscillates with which should not be too large in amplitude. Otherwise, the hydromechanical system may lose stability and collapse. Therefore, vibration control and actions to reduce vibration are very important. Simulating model of rotor systems is impossible without the use of specialized software. MATLAB Simulink together with SolidWorks allows modeling multi-body system. Then we can add some specific models of the fluid flows to calculate lifting force using our own programs. Also, we can use toolboxes to implement machine learning, for instance. And one of the most important advantages of MATLAB is the possibility to connect software and hardware. This is very useful in design of measurement and control system. So we have complex mathematical models and powerful software to solve complicated problems in hydrodynamics. And it's hard to realize that we can't accurately model a cup of tea because it's difficult to set boundary conditions. The cap and the spoon are the boundary in the problem of the fluid flow, or tea flow, I mean. In the motion of the spoon is very complicated and depends on the arm motion and the shoulder motion and so on, and even depends on that person's feelings. The accurate mathematical model becomes too complicated. I can't solve it, and I should live with that. I think this is similar to Heisenberg's uncertainty principle. The more accurately we know position of the particle, the less certainly we know where it moves to. So the more accurate the physical correspondence to the model to the object, the greater its computational error. Well, it looks like a joke because it mostly is a joke. A different approach may partially resolve the contradiction and expand the possibilities of modeling. What I have told you earlier related to the deterministic approach. That is, it is believed that the laws, equations, etc. are known for the process under study, and those equations need to be solved. The process is a white box, and it's clear for us what is in it. The other approach is based on the analysis of observed data without specifying the reasons. In this case, the process is a black box. This approach is called stochastic. It has not been taken seriously for a long time, I suppose. So far, the success of artificial neural networks has not become apparent to all. We realize that they can no longer be ignored in 2016. Since then, we have made a classification of tasks that can be solved with the use of artificial neural networks and began to do them. The first task we did was approximation of hydrodynamical forces in the fluid field. The main objective of approximation is to find the function h that best describes the dataset, and the main idea to minimize the loss function and find the best values of the theta parameters. This is similar to seeking the deepest point in a lake with muddy water. The most common method is gradient descent. In artificial neuron, the set of input numbers u is multiplied by the weights theta, then sum it up, and finally the activation function is applied. The result is output value. The use of the activation function and neural cooperation in the computational network makes the neural network an excellent approximator. Following idea is to minimize the loss function and find the best values of theta parameters using backpropagation for gradient descent. In our task 1, we used fit for all neural network with 4 input neurons, one hidden layer with 10 neurons, and sigmoid activation function, and 2 output neurons. The network was designed in MATLAB and Stack. The dataset for RNN we've received from our simulation program of Rotor dynamics. We took about 100,000 points for dataset. Then we trained the network to approximate the dataset and get very good results. Trained network works very fast, much faster than our previous simulation program, and its calculation time is even faster than real time. The neural network program model can calculate 10 seconds of rotor vibration in 7 seconds. The application of the ANN to calculate lifting forces or some other physical values is very promising, but the main disadvantage is low computational accuracy in extrapolation. Talking about this specific case, it can calculate the same or the smaller amplitudes than were given in dataset, but it can calculate bigger ones. The next network can fix this problem. In the next task, we use nonlinear autoregressive with external input, so-called NARCs network. Network like this commonly used to predict time series. The network feature is to use past values of output together with input for learning. The network was also designed in MATLAB and Stack. We received the dataset for RNN from proximity probes of the test rig with high-speed measuring system. We trained the network and then tested it with new dataset. The results were good. Please note that the previous network can't, the previous network can't calculate extrapolation, but this network can do it well. I believe that NARCs networks could be very useful to predict time series for rotor machines to avoid failures. The main disadvantage of NARCs is that they can't approximate the function of many variables. The next task is connected with pattern recognition and classification. Usually, classification problem connected with logistic regression. The main objective of logistic regression is to find the function h that best describes the binary function y of continuous argument u. To solve this problem, it's easy to replace the variable u with z to define the class boundary z is equal to 0. The logistic function can be used. Similar actions are performed for functions of many variables, and the main idea is to minimize the loss function and find the best values of the theta parameters using gradient descent and backpropagation, just like in linear regression. In our task 3, we used fit-for-all neural network with 2 or 3 input neurons, one hidden layer of 10 or 20 or more neurons, and sigmoid activation function, and 4 output neurons with softmax activation function. The network was also designed in MATLAB. We received the dataset for ANN from proximity probes and pressure sensor. We mixed cold and hot water and tried to achieve nonlinear effect of lubrication. The bad news is that we didn't get a clear visible effect using visual analysis of frequency response. All the trajectories look random. And the good news is that the ANN catch the patterns of 4 given classes very well. The accuracy of the network was higher than 90%. So, the network like this can be very useful in diagnosis of machine. The following task is connected with control. Solving this task, we used learning in interaction with machine. In previous task, we used supervised learning because we had the labeled dataset, but in this task, we didn't have it. The main objective of reinforcement learning is take a correct action on the basis of current state of environment. The main problem is that the correct action are unknown sometimes, and the main idea is to train agent after the event when the result is obvious, and to give him higher reward for the better action. The game of Pong is an excellent example of a simple reinforcement learning task. The network takes the state of the game and decides to move up or down. The network plays 100 games, for example, and if it wins, then all decisions were correct, and if it loses, then all decisions were bad. Then, as usual, we can calculate loss function, its gradient, and find newer values of network weights. In our task 4, we used deep deterministic policy gradient agent, which was designed in DeepMind walking simulators in 2016 and in MATLAB Deep Learning Toolbox in 2019. The DDPG agent includes two networks, the critic network and the actor network. The critic network minimizing the loss function to find the biggest reward for all subsequent action, and the actor using the critic to calculate gradient descent and to determine next action. We used multi-layer neural network with ReLU activation function for the critic and for the actor. As the environment, we used simulation program and the real test rig. In the case of simulation program, simulation environment, we use the network from the previous task to calculate the lifting force and the friction torque in the bearing. And also we used SolidWorks together with MATLAB Simulator to create the multi-body model of the rotor bearing system. We set a random external force and calculated the oscillation and energy consumption. Then we trained the DDPG agent. The agent got about 2000 penalty epochs when learned how to minimize energy due to friction and vibration. As the result, the active control system allowed to save about 70% of energy in rotor machine. At the next stage, we started to train the DDPG agent in interaction with real test rig in real time. This work is ongoing because the training in a real takes a lot of time, so we keep trying and keep going. Well, this is it. Thank you very much for your attention.